So go ahead and yeah, so 7, 8 minutes and no questions. I'll go from there. So, okay.
Right. Okay, so we all love QCD, right? Like it's an amazing theory, lots of predictive power, but also very difficult, right? And a lot of mysteries remain unsolved. One of those pertains to core confinement or hadronization. So we've been able to measure, well, we can measure directly color neutral states. That means hadrons, but we cannot measure directly colored states, such as quarks and gluons. But provided a sufficiently large energy in nuclear collisions, we've been able to probe and get a glimpse of a very brief indirect measurement of a deconfined state, such as the quark gluon plasma. But now, given the amazing machine that is the EIC, we can ask ourselves this following question. How can we explore hadronization with this machine? And turns out the EIC will provide a unique opportunity to understand hadronization much, much better. And the way that we will do that is by importing many of the tools from heavy ions, from like jet physics and deep inelastic scattering. For instance, let's go to deep inelastic scattering. What does it happen here? So we have our the electron interacting via like a virtual photon with one of the partons inside of the proton. Then a bunch of hadrons are produced. And we think of this because I mean the proton is really tiny, and you can argue that the hadrons will be produced outside the proton, or it doesn't really matter. So it is, I want to focus on this stage because then you are transitioning from a colored state to color neutral states. In other words, you've transitioned from, you've undergone hadronization, and we can probe that. So in the Lund string model, as some of you may know, quarks and antiquark pairs are bounded by a string that has a linearly rising tension. When this tension is large enough, this string fragments and a bunch of hadrons are produced. A shower of hadrons are produced. So this point in space-time is the initial creation of this quark-antiquark pair. Then the strings are fragmented at different points in space-time. And each of these filaments represent a hadron, for instance. This is the model that is currently implemented in Vithya and regularly used. And the time that it takes from this initial point to the hadrons forming is called the information time. That will be important. But now, if we scale this up to the EIC, that means like electron-ion collisions, we can ask ourselves the following questions. How will hadrons or strings interact with the medium? Now, the medium is much larger than a single proton. Like if the medium is large enough, for instance, a Fermi or more, well, the medium is going to be around 6 Fermi for heavy ions. Can hadrons, which will have like a characteristic length of around 1 Fermi, will they have time to form inside or outside the nucleus? That's one of the questions. And we will do this in the following way. So remember the formation time that I spoke about? So this is basically the same plot as before. We can do that by parameterizing the cross-section as a time-dependent cross-section. That means if this is just the normalized cross-section, this F. If this normalized cross-section goes to 1 very rapidly, that means the hadrons will be produced very instantly. Thus, they will be produced inside the nucleus. Or if the formation time is very large, then the hadrons will take a long time and they will be absolutely produced outside the medium. Or you can have anything in between. So this has been explored already by some preliminary results, preliminary studies that have interpolated this with simple parametrizations like linear, quadratic, and so on. So the results are inconclusive, but the data is promising. For instance, here is these are the yields in producing these type of reactions in heavy ions, and you can see that different parameterization corresponding to different curves in this plot yield different results, right? So this is an important prediction. Now, how can we do this in a more systematic and more evolved way? We can do this by creating a new event generator, and this will be the event generator for the SURGE collaboration. And what this means is that we will couple a hard scattering phase with a soft scattering phase. The hard scattering phase will be used using E-hydrogen and the soft SMASH. SMASH is a hadron transport approach used in afterburners in hydrodynamic hybrid models. And so what I'm doing is creating tabular time-dependent cross-sections, such as the ones that I showed before, fitting them into SMASH. This takes charge of like the hadrons evolving in the medium, then coupling them together, and then perform Bayesian analysis to see what of these time-dependent cross-sections is favored by data. For this, I will borrow one of the ideas, the recent ideas used in the neutron star community, where they use Gaussian processes to create several functional forms for the speed of sound inside of neutron stars. So Gaussian processes, for the people that don't know, are just like a useful tool, machine learning tool, to create like basically at random or variations from the mean of a mean behavior. So we seek to replicate this for our problem. So remember this this plot that I showed. Now we want all the possible like interpolations between these 2 points. Don't worry about all these forms, but this is basically we're embedding some of the physical information into the model. For instance, we want a linear, a rising, monotonically rising cross-section. We don't want cross-sections to go to negative numbers and so on. They have to be normalized. So this is a physics-informed machine learning tool. And this is the result. We can create thousands and thousands of these time-dependent cross-sections. Now, I'm planning to use, this is an ongoing research project, so I'm going to use a Bayesian analysis study to try to constrain what the formation time is in these reactions. And I will be using, eventually I will be using EAC data, but I can also use HERA data. And as conclusions, we are studying hadronization via this new model agnostic approach, which is based on previous knowledge from heavy ions and jet physics. We will be using like novel approaches, such as Gaussian processes, and more importantly, we will have an event generator for the SURGE collaboration. That's it.
Thank you. Interesting. Is it, will you be able to compare this with, for example, the standard Lund and see the difference? Is that one of the features?
Exactly. For E-hydrogen is basically a modified version of Pythia.
Mhm.
And the nice thing of E-hydrogen is that it already has built-in like nuclear TMDs. Basically, the interaction rate, the collision rate is proportional to the TMDs. So you have information of the medium, the nuclear medium.
Yeah.
You will be probing saturation, for instance.
Yeah, and it's very, very interesting to see what extra this has.
Exactly. This is more than Pythia.
Are there other questions? Yeah.
We've currently done for, I know it's, this hot environment, but like BPA, like, how to qualify? In PP and AA, how
Yeah.
the hadronization model modified? There's a different thing that you're trying to do here, but I was just curious.
Yeah, so it's very different. What we do in heavy ions is mostly what Jacine explained. Like it's mostly this jet propagating in the medium. So but the hydronization of the fluid is done using an entirely different approach called the Cooper-Frye formalism that turns like fluid cells into particles given a distribution, a Fermi direct distribution.
Thanks, Jordi, again. So switching.
Yeah, sorry about that.
Go back to here and then try and do the screen. I'll give you what, you know, when to 3 and 5 minutes.
Yeah, so 1 second. 1 second. Okay. Can I play with this and then get ready? I was like, just,
The top one is the pointer. Recording that.
okay, okay. Okay, I see. All right, so, hi everyone, sorry about the last minute change. But so actually you set me up pretty nicely. I guess it kind of goes back and forth between us in terms of doing a little bit more of a hot topic, not only because I think it's really cool, but also like we're talking QGP. And so, but today I'll talk about strange and multi-strange hadron production in heavy ion collisions. So a little bit of a background is, so we're going to change a little bit of gears. And then right now, a lot of the time what we've been talking about, we haven't really cared much about QGP. But this is the idea here is that in this high temperatures, this QCD matter becomes a new state that we call the quark-gluon plasma. We predicted its existence in 1975, but it wasn't discovered experimentally until the 2000s. We also believe it existed in the first microseconds after the Big Bang. And there's a lot of work trying to really understand the phase diagram of QCD. And so what I'm focusing right now is around here. And then there's other, if you go to high baryon density and low temperatures, like in neutron stars, we also see that formation. I don't work with that, so that's all I have to say about this. Okay, so how do the heavy ion collisions work? Well, first, you pick your nuclei. There we go. Pick your nuclei. You accelerate them to speeds close to the speed of light. And so then in this part, the ions become contracted and these like discs or tortilla-shaped objects collide. You get a QGP forms, and then it rapidly cools and expands. Then at this point, the partons hadronize and become a system of interacting hadrons. That's your jam. So right now, I don't focus so much on that. And then we call this the transition temperature here, where, God, sorry, here at this point is where the temperature of the particles and the momentums is fixed. And then from there, we actually end up in the experiment. Okay, so all of this is happening really, really quickly. Sorry. So there's 2 existing colliders in the world that can recreate the conditions for QGP. You have one right here at RIG with STAR and S-Phoenix, and our top beam energy is 200 GeV. And then there's also the Large Hadron Collider with a top ion like beam energy for heavy ions of 5.36 TeV. And there's more experiments, and the really dedicated heavy ion detector is ALICE. ALICE was built just for this, but then all of them have a heavy ion program regardless. Okay, so I work with STAR, it stands for the Solenoid Tracker Rig, which has been operating since 2000. It's 25-year anniversary. It's a time projection chamber that has a methane argon mix, and that's how you reconstruct the tracks here. No, this is harder than I remember.
There's a stick down there if you.
Okay, I might do that, sorry. Yes, so this is the TPC. And then that's the main detector that I work with. And then we use that for PID, and then we also do the time of flight. This is like a simulated event. This was me in 2019 before I started graduate school. Anyway, I always think that's a funny picture because that was way before I ever thought of joining STAR. Okay, so for useful coordinates, this might not be, you already know this. We measure PT. This is beam coming in. Measure PT in this plane, transfer momentum. You get this angle that we can talk about with pseudo rapidity. And then the last thing for my topic to make sense is this talking about centrality and multiplicity. Okay, so the nuclei have a finite size, and though we try our best to have them collide head on, sometimes it doesn't happen. And so the distance between the centers of the two nuclei is what we call the impact parameter. And we cannot measure that. We don't have access to this measurement. So instead, what we can do is see how much activity an event had. And that allows us to split these collisions into different centralities. And so that instead is what we call the proxy for impact parameter. So you see, this would be how many nucleons participated, and then these are expectators. So this would be like a mid-central collision. Okay. And so a smaller impact parameter corresponds to a more head-on collision, which means you have a high multiplicity. Peripheral, you have a higher B, and then that's when I talk about 40 to 60 centrality. Or low multiplicity, I mean like events that weren't as head-on. Okay, I'm going, yes. So the other thing you want to talk about is strangeness enhancements in the QGP. That's because strangeness enhancement was actually one of the first predicted observables as a signature of the QGP. You might wonder why. So for my fellow theorists, here are your Feynman diagrams. And so when we talk about the thermal production of strange and anti-strange pairs, there was this paper in the 70s, in the 80s, that proposed that the thermal production of the strange and anti-strange quark pairs is favorable because their masses are lower than the QGP temperature, which is about 300 MeV, but it's also really close to the transition temperature from QGP to hadron gas. So you'll have a bunch of gluons around, and so it's really easy to create through the gluons, get these quark pairs. Okay, and the threshold energy to make a lambda is pretty high. So we believe that multi-strange hadrons are extra sensitive to the existence of QGP. Okay, so everything's nice. We see an enhancement of the strange yield to the ratio of pions. We believe that that's a signature of QGP. It was great. You see that in proton-proton collisions, we don't see this enhancement. Experiments in different energies also see it. We understand the picture. That's what we thought. But then in 2017, Alice published these results in which what they showed is an enhanced ratio of strange hadrons to pions in high multiplicity proton-proton collisions. So what do I mean? So as a function of, in the x-axis, I have multiplicity, and in the y-axis, I have the ratio of whatever this particle is divided by the pion yield. So and as I go down in the y-axis, I'm increasing my strangeness. So the K0 short is we can't tell because it's neutral. We just counted for 2. So what you'll see is that there's really a smooth transition going from PP to P-lead to lead-lead. Okay. Then we look at the lambdas. So what you're seeing is, okay, lambdas, higher mass, okay. Again, at the lower multiplicities, we have a proton-proton, and then you can't really tell which system is which. And this smooth transition was really surprising. Then the other thing to note is that models can't really recreate this that well. Okay, but lambdas only have one strange part. What happens if I go to x's? Okay, so then I can draw like this slope, and you see the same trend for the x's, that then I have two strange parts, and then the omegas where I have three. This was really surprising. And so the fact that there's no sudden onset for the QGP was really surprising, and models aren't able to recreate this data very well. Okay, where do I come in? So star might be able to see the same. The problem is that star in this low multiplicity region, we don't have a lot of data, which is exactly where the slope would be happening. But the cool thing about RIC is that it's really able to change nuclei, not only energy, but also size really easily. And so in 2021, they did an oxygen-oxygen run. And this is really nice because not only is it a small nucleon, but it's also symmetric, which allows us to have a more straightforward geometry mapping than in terms when we talk about centrality than in other asymmetric or small systems like helium gold or deuteron gold. And so our oxygen-oxygen can really help extend this unexplored region from its most central collisions to its peripheral collisions. And then part of it is we can close this gap. We've compared, these are some preliminary results that I've showed at a different conference. We compare the oxygen yield in its most central bin to other published data for a similar end part, and they agree within uncertainties. I can post a link to where these are anyway, but there's a lot of oxygen-oxygen measurements that are presented in Quark Matter. You should check them out. But also there's a really interesting opportunity because LHC is supposed to do an oxygen-oxygen run later this year. And that's the first time where we can have a direct comparison between the two. And I think that was the last one. Yes, it is.
Thank you.
Yeah.
This is the other strange puzzles going on. We have time for a quick question, sure.
So given that oxygen is so small, do you think it will achieve the thermodynamic limit in order to use HRG to compare, or?
Are you thinking like thermal models?
Yeah.
I think, so that's my goal. That's part of what I really wanna, once we finish all the yields, I didn't show them because then I would, getting what's it called, approval to show talks takes a bit, so I didn't show any on purpose. But yeah, so once I have all the yields, it's really interesting to see what's gonna happen. Like we're comparing to generators, Pythia doesn't do a good job at modeling this because it doesn't assume any medium, right? So seeing how that comparison looks, looking at thermal models, looking at other generators that do model the QGP, I think that would be interesting. I don't know. I think we're kind of in the limit of it's small, but maybe. So we'll see. I don't know. I'm not sure what to expect. I hope it does. I hope we do see the nice slope. I think that'll be really interesting. Or if we don't, if you go to LHC when they have a higher energy density and see what happens there, I think that's also going to be really interesting.
Let's thank our scans.
Yeah. And then, oh yeah. So the top one is this, and then forward and backward. See, that's all.
Product pointer is better than one.
No, I think the pointer should be the biggest one. Yeah, see, so the pointer is the first one. And then to go back is the bottom. There you go.
Thank you.
So, okay, right?
Yeah. Good afternoon, everyone. I'm going to discuss the work that I have been doing with the EIC for the time of flight detector. So just a quick recap. All of you have seen this picture before also. So these green color are the polarly detectors designed with the purpose of having PID. So right now in collider physics, EIC will have it is supposed to have best PID detection. For PID means particle identification. So it is designed to have a 3 sigma particle identification. Particularly, time of flight will come into picture below 2 GeV of the PT. And along with the particle identification, it will provide XYZT for 4D reconstruction of the events. So this part is for the Cherenkov detector, and this particular green region is where the time of flight detector will be located. This is the Jianford geometry that is being made using the DD4HAB package. Now everybody, I think, is familiar with the DD4HAB since Saqib has given the glimpse of how it works. And the time of flight detector has two parts. One is the cylindrical, that is called barrel, and one is this end cap, that is forward or end cap, whatever you may use. This is the beam, and these are the direction of electron and proton beam. So my work is particularly concentrated on this part. The disk that you are seeing, that is called forward time of flight detector. This slide is just to get the dimensions, how big is the detector is. So I will concentrate on end cap. So this part is the inner radius with having 10.5 centimeter. This is with the outer radius of 60 centimeter, and you can see that it consists of modules. So this whole part will consist of 386 modules of size about 4 into 4 mm square. I will tell what all these things are there in each module, and it will here I am taking the z direction as parallel to the beam. So you can see that this will be about 7.5 centimeter in thickness. These are the sensor. That is one of the you can say biggest achievement for particularly in the terms of timing resolution. So time of flight will be using AC LGAT sensor, capacitively coupled low gain avalanche diodes, having the excellent timing resolution. It is really difficult to achieve this timing resolution along with the spatial resolution of 10 micrometer with high granularity. So this granularity will help us to achieve we can distribute the charge among the cells so that we can get to know precise position of the hits. One thing I would emphasize, that this layer, I don't know whether it is visible from there, this particular layer is what decides the resolution of the sensor. So this is supposed to be thinner so that electron can cross it in minimum time, so that the timing resolution can come more down. But you cannot do just arbitrarily thinning. So you need to optimize lots of things. So this is one of the specialty that you can get high timing resolution along with the spatial resolution for ACL gates. So these are just specification of the time of flight. I will skip this thing. The only emphasize that I will put on is timing resolution for barrel and forward. Forward will have even better than the barrel one. So this part is for barrel. I will not go with this. So this is for the end cap. So you can see this is a sensor which will be mounted with the ASIC. ASIC is a CPU thing that will be used to get the signal from the sensor, and then it will be mounted. Three of such sensor will be mounted on power board. Then this will make a readout board, and 4 such unit will add on to make one module that I have shown earlier. Like one side of the end cap will have 386 module, and the other side will also have same number of modules. So the goal of my simulation that I'm doing is to extract hit information, that is 20-bit decimal number, and then finding the neighboring cell and implementing the smearing in the energy using 2D Gaussian. And then this is a little bit tricky and complicated part, that is implementation of digitization of energy and timing information. And then to mimic the data, we need to add noise, that we are planning to go with the Gaussian random numbers in the simulated data. So how do we get these hit cell IDs? So now I think everybody is familiar with the NPSIM, because everybody has used this command in particularly first 3 days of the tutorial with the Saqib. So what I'm generating the events of 100 to 10 to 100 GeV electrons, and then I'll get a hit, which will and Gian4 will provide a address of that hit in terms of this much big number, and this is converted into 64-bit binary using the binary conversion. And the DD4 is having advantage of decoder, because Gian4 decoder is not there. In DD4 you can convert this 64-bit digit number into this full address of the hit. like which system number is being used. Like for particular, for first 8 digits will tell you the, when you will convert it into decimal, will give you system number, that is end capped off, then layer number, module, XY IDs and sensor numbers, etc. So this will be the full address of the hit that you will get. Then I'm using the segmentation function that is already also again there in DD4HAP to know the number of neighboring cell of hit cell. So in this plot, x-axis is the time forward time of flight dimension in terms of millimeter, and this is the y-axis, y coordinates of time of flight detector. So this is one hit, that is the red dot, and then these are circles are the neighboring cells for that particular hit. And once I know the neighboring cells and their dimension, like where they are, how much they are having distance from the central hit cell, I will implement 2D Gaussian. So I will define a function with the parameters from 0 to 4 and EDEP. EDEP means the energy deposited in that particular hit. I will use it as amplitude. Then this X position hit, Y position hit, from like what will be central position of the hit, and then these are the sigmas for 2D Gaussian. Here I'm taking 1 and 50. Let me tell you, 1 is more reasonable than 50, but since in 50 you can see the exaggerated image, how the smearing looks like. So for that purpose, I have kept 50 also. And once we have implemented, then to calculate a complete charge correction, I will integrate this Gaussian from the limit of extreme neighboring to like the neighboring cells that I'm calculating from top to bottom and left to right. And then we will store the information of the charge hits. So this is what looks when the sigma is 1. These are again the x and y coordinates of the end cap. This is one of the hit. You can see the scale of energy deposition. So the central one is having maximum energy deposition, and as it spreads, it goes down. So this is with sigma 1, and this is same hit with sigma 50. But this is just to exaggerate. This is not a reasonable number, just to make you feel that how actually energy is deposited when the hit goes in the detector. So the next step to this is to digitize the hit information into ADC and TDC, and adding the noise to the simulated data. This I'm still working on. Any suggestion, any like discussion on this are most welcome. And yeah, this is the summary. I have completed these particular 3 steps, and right now working on this. And once it is done, I'll go to the adding to the noise to the data. That's all for me. Thank you.
Yeah, thank you. It's an interesting. Thomas showed the kinematic maps to the detector, and it's, you really need the precision, especially in the end cap. So thank you. Good. Any questions for Michael?
Thank you. Congratulations, Honey, for your presentation. I have a little question. If when you show 2D Gaussian parameterization, it is possible to get only one parameter, the denominator of the exponential function?
See, when hit goes. So suppose if it is like vertical hit, that time it might be symmetrical. You can take 1 sigma, right? And suppose it goes at some angle, then this spread will be more as compared to vertical. So you need to
two parameters.
Yeah.
Yeah.
And that also right now we are taking a number, but because we are still working on the characterization of SEL get. So till now we don't have any that like practical number, but 1 mm is more reasonable than 50 mm. This I know.
Thank you. So thank you again. You can use high-tech or low-tech pointers as you like. They'll give you 3 minute, 1 minute.
So hi, everyone. First of all, I want to thank the organizers for organizing this wonderful school. And I'm very glad I met you all and interacted and talked about some good physics. So my name's Brandon. I'm Yuri's student. I'm going to be talking about orbital angular momentum at small x, and this is based off these three papers here. So the first question, well, the question I want to answer in this talk is why OM at small x? Well, as you saw from the spin puzzle talks, whenever anyone talks about this proton spin budget, they leave out this big section here, which could be from the spin contributions, but equally important, it could also be from the OAM contributions, which currently we know nothing about experimentally. So there's no data that gives us info about the orbital angular momentum contributions. So that's why OAM. Now, of course, most of you know at small x, you can't, I mean, because x is proportional to 1 over energy, you can't probe all the way down to x equals 0. So of course, we need small x evolution to tell us what's happening there. And I've just put the plot of polarized measurements, and we can see EIC will give us better coverage, but of course, you can just keep going in x. So we need a good handle on what's going on down at small x. So how does one approach OAM in QCD? So hopefully you all know in classical mechanics, right, to get orbital angular momentum, I take some moment inertia and I multiply by the kinematic structure, the angular momentum, or the angular velocity in this case. So I encodes the structure of whatever object you're looking at. And so how do we go to Q of t now? Well, we do the usual thing. We make everything operators and we add integrals. So that's what we did here. So you can see the orbital angular momentum distribution is now this I function times a kinematic factor k. So this I function is related to, it's defined here, it's the first impact parameter moment of a polarized dipole amplitude. So this polarized dipole amplitude is the spin, so it exchanges, it depends on the proton spin, and it's the polarized analog of what Yuri was talking about, this n dipole amplitude a couple days ago. And just to remind you, we have an impact parameter b inside the proton, and then there's the dipole size r. So this is a new object. It's the moment of these dipole amplitudes, and so it's a different object from just an impact parameter integrated dipole and deserves its own study. So how do we evolve things? Well, the master himself showed how to do it. So we take this dipole amplitude, and then to evolve in energy, we allow these slow gluons to traverse the shock wave, and we can sum up all the types of ways we can do this, and that gives us a differential equation for the energy dependence of our dipole amplitude, which then we can plug back into the formula before and get the energy dependence of the OAM. So, so we constructed those and we solved them in these papers. And one thing you can show in the small x limit is that the OAM distributions have the same asymptotics as the helicity PDFs. So going back all the way to the first slide, that means at small x, they're just as important and could potentially fill in the rest of the proton spin budget. So they're very important to get a handle of. So the next question is, of course, how do we measure these OAM distributions? Well, if you remember from Yoshitaka's talk, L roughly is B cross K. So it's some cross product of two transverse vectors. Well, if you start thinking about what processes have two transverse vectors, maybe the easiest one you can think of is dijets. You have two jets, two transverse momenta, and therefore we could potentially probe the OAM distributions. So just to remind you, this is what a dijet process looks like in small x in EP collision. So you have the electron, you have the photon, you have the proton, and then you also have the two jets. So the two jets momenta I call P1 and P2, and then I define the jet momentum imbalance, P, and the transverse momentum transfer. Well, written here, it can be anything, but transverse momentum transfer delta. So I can compute this process and expand as a function of delta. So I'm looking at the small momentum transfer, and you know how all these exclusive processes drop as a function of momentum transfer. So this is where the data is. And I noticed that this the linear term in the momentum transfer, I can show is proportional to this moment amplitude, and therefore accesses the OAM distributions. So, and this has been concluded in these papers here. So the conclusion here is if we look at the dijet process and we look at these angular correlations between the two jets, we get access to OAM. And so this is a theoretical calculation, and now one has to go and check that one can actually do this. This is an exclusive process. I don't have time to talk about why, but we want to consider an elastic scattering so the proton stays intact in the final state. So there's a question of, can we actually measure this? Do we have enough luminosity and at the EIC, and what energy ranges would we be able to see this? And that's what I'm working on now. So feasibility study and seeing whether this is possible. But in principle, it is. And hopefully when the EIC turns on, we can get a better handle on how OAM fits into the proton spin. So thank you.
Tricky connection, but it gives you an angle on it. So
Yeah, it's convoluted, but it's here.
Nick?
So the orbital angular momentum there, is B-perp still the impact parameter of the dipole against the proton?
Yeah, here, yes.
And
So-
A-perp, would that be, there's two jets,
Yeah,
but
So
there's
K-
only one K-perp there.
yeah, K-perp is related to the definition of the OAM distribution, but here you can think about it as the jet momentum imbalance. So it's this P, which is, I mean,
One
these,
K-perp from, as like a measurement from both jets.
well, you could think about K-perp as the difference in the momentum between the two jets.
Okay.
Let's thank Brandon again. Our final talk of the session is, there we go.
It's even one. Yeah.
Yeah.
All right, you can, yeah, the
Yeah.
top one, it's a little slow, and I'll give you warnings. So about 8 minutes, give you warnings at 3 and 1 minute, so. Okay, all set? All right.
Great.
So, hello everyone. My name is Matheus Guilherme. I'm an undergraduate student at Unicamp in São Paulo, Brazil. And today I'd like to talk just briefly about what I've been developing the past 6 months. So, yeah, there you go. I think that to start is very important to begin with our motivation and objectives. So, oops. Okay, so in high-energy physics, we know that Monte Carlo simulations are widely used to just set selection criteria and just basically enhance and try to improve your efficiency in a real experimental data analysis. However, these complete event simulation using Monte Carlo techniques are very computationally expensive, and they take a largest amount of processing time. So therefore, we aim to break this cost established by the Monte Carlo simulations by proposing the use of generative machine learning methods so for synthetic data generation. So we seek to essentially synthesize secondary decay particles, which I'll try to explain better throughout my presentation. So to begin with, what exactly is machine learning? I have a definition and a nice picture for you guys, but I'll just, in essence, explain that machine learning is what we try to make the computer think as a human. So we try as best as we can to just make the computer learn from experiences, to the computer mimic the human behavior of learn from experience. So that's basically it. So what can we do with machine learning? We can do generative models. So we can build variation of decoders. We can build city GANs in general, and diffusion models. Those are all generative models that have the primary goal of just generate synthetic data. So this is more of a technical details. We can see that for the city GAN model, we use 4 fluid connected layers with 256 neurons. and we train over 500 epochs. And for the diffusion model, we use 6 layers with 1,024 neurons each, and we train for 1,000 times that. And for the VA, we use the optional Python library. For those who don't know, it's a library that able us to automatically search for the best parameters that the model can use. So we can see that there's a lot of difference between the models, and that's just because each model has its own algorithm and so forth, so forth. So going to the methodology, we have a 2.5 million event Monte Carlo data set of PP collisions, and approximately we have also 16 features, including kinematic features, which is the momentum of the photon and the lambda in this case of the decay of the sigma zero. And we also have plus 10 topological variables, which would be something like cosine of Ponce of the lambda and the photon, and also like distance of closest approach and so forth and so forth. We are interested in this case in the sigma zero topology, for example, but it could be any other particle, it doesn't matter, because we are only interested in working with the background data. That's why, and we do that because in the analysis, for example, we are interested in suppressing the background as much as we can so we can have the signal. And since we are trying to optimize the analysis, we are just worried about the background here. So after all that, we improve our model parameters, we train the model and evaluate the results. That's just that. It's so here we have some results from the statistical model. We have two histograms here. Sigma zero invariant mass spectrum. And we can see some decent results. We can see that the model is trying to synthesize the shape of the background. Usually that would be a peak over here because we're talking about sigma zero, but since as I already explained to you guys, we're just working about the background, so it is supposed to look like that. And over there we have like one of the other features, and we can see a difference between Monte Carlo and synthetic data in low px of lambda and some fluctuations over the ratio between the two distributions, which is expected to happen because of the way of the citizen actually work. It's called mode-specific normalization. I can explain later if I have enough time. But moving on into the diffusion model, we have some better results. We can see that the model learns better and give us better results to trying to learn the shape of the background and also the shape of the px distribution of the lambda. But we have to be careful because in this data set, I've only used 6 features, so it's a 6-dimensional data set instead of a 16-dimensional data set, which is the whole data set. Just because this is our early results, so it is more like a toy model, but since the diffusion model is supposed to be even better than the GANs and the VAEs, I wanted to show you guys because those are really exciting and just promising results. And okay, to wrap it up, summary. So we have explored and implemented the generative models such as VAEs, GANs, and diffusion models. We have shown the ability of most of these models to learn complex unstructured data. And one thing that I didn't mention is that I didn't show any VA's results because we were unable to make it learn the complex data that we have. So that's all I'm saying, most of the models. So therefore, we have demonstrated that CTGA and the diffusion model can generate millions of data within seconds. Once I have my model trained, I can generate millions of data in seconds instead of hours or even days of simulations. And that's the crucial point of all this work, is to optimize performance and statistics. And so next steps is just to engage in a PhD project. I'm graduating this year, so that's it for now. And I hope I did that all. No, 10 minutes. So thank you very much.
Good luck with the PhD project. Hopefully, I mean, we saw Nobu showed the, some of the applications,
Yeah.
these things. Do we have a question or? Oh,
So, experimentally differentiating between sigma 0 and lambda 0 is really hard, like basically impossible because the decay times are so short. But I know that you're focusing more on I guess you're only focusing on the MC part, right? Then it won't matter as much for your stuff. Or have you thought of that? Or I guess your idea is more of just how to
Yeah, the idea is just
simulate them more, right?
just to in principle just to generate data that realized in the physics of the decay, but really worried about the experimental aspects.
Right there.
all right, other questions? Let's thank all our speakers again and so what we'll do now is we will trade in your cards for your certificates. So we're going to do that alphabetically. If you come on up, let me grab my pen. And Socorro and Melissa hopefully will be here in just a moment. I'll give you a chance to thank